Okay, we'll start with the class. So we have to continue from deep learning, and we have to see today few things like confusion matrix and the LSTM, how we implement and how we use confusion matrix. So I'll be using first going to confusion matrix. This actually is used to check the accuracy and how well the data is classified. Actually, classification accuracy you can get it from here, or just looking by at the matrix you can make out that the class are properly done or not, or the data is properly classified or not. Okay, so we'll be using a very simple example, and then we'll be using the real data set also. So let's have a small example with this data and some label. Let's say we have given some class. So for that, first of all, I have to import TensorFlow. Okay, so I'll just copy paste. Import TensorFlow as TF. This could be anything. Instead of TF, you can give anything, but normally we use TF. So it's easy to read, others can understand. Okay, so we have imported that, and then we can put it direct like tf.math.confusion, tf.math. I think it will come on its own. It should fusion. You can put it directly. You can put it in variables and do that. And now we need the data. Suppose we have 1, 2, 3, 4, and the label or the class predicted value. This is the real value. This is the predicted value. So predicted could be like something like 2, 3, 4. Now if I run it, this is the syntax here. The label predictions. These are the labels and these are the predictions. This is actually the real labels and these are the predicted labels. You can say that. There's some issue. Let me see. I put one extra. Comma 2, 2, 3, 4. That's fine. Okay, so you can see here that you get a shape of 5 by 5. So what you do, you get one extra, at least square matrix you get, and that was 4 by 4. Later you get 5 by 5, one extra is there. Now you can see that the matching is not in the first two rows. They don't. The data is not in the diagonal. So if all the data fall in the diagonal, then you can say that the classification is proper. If it is not, the classification is not proper and your accuracy would not be 100%. This would be somewhere around 95, 97% accuracy. Only one data is missing. It's going here. You can see that one here. The rest are here in the diagonal only. So let me change this data and see what happens. Be able to understand it better with a different data. I'll just put everything as it is, the original and the predicted. You can see all falling in the diagonal. First is extra, that is header types, and then you can see that all are in the diagonal. That means this is 100% accurate classification. And if I change it further, I make it 4, 3, 1. Although the numbers are there, but not in the sequence. So let's see. You see that it does not match. the labels are not correctly classified. It's nothing. It's almost zero. Accuracy won't be there at all. There's no match. There's nothing in the diagonal. The major diagonal is now 0, 0, 0, 0. That means not a single class has matched. So from the confusion matrix itself, you can actually make out how your classification is behaving. You can see. Okay, so you can work on the variables and you can see that values. You can use different values. You can use. So let me put it labels and right. So if we have labels like we have to convert it actually into constants in 32. That is this is a list actually which is inside, and I'm converting it into tensor. So I'm using tf.constant to convert it into a tensor type tensor type rather array. And predictions, labels and predictions. That is, labels is original, prediction is the predicted data. I'll just change it to original. Let me make it smaller. Something like this you have. Okay, I'm just printing the data you have. So this is the data you have. Now if you apply now your confusion matrix on this, and see, this is not labels, this is original. Okay, so if you have original and the predicted, and now we print, there are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, because the expected 9 is their shape is 9. You can see that. So in the diagonal, you can see that some of the data is not matching, right? And here also you can see that the labels are not exactly what they were. 1, 2, 4, 5, 6, 8, 9, 10. And where here we have, there's one extra 10, okay? That's why the shape is 11 now. 10 is not there at all in your labels. They have to be of the same shape, keep in mind. They cannot be of different shapes. Okay, so if it is 9, it has to be 9 only. So 9 elements. Because when we predict using machine learning or deep learning, so it will be of the same shape. You can see that it is not matching. If I change now, let me change this. Let's put the data and confusion. Also, we normally use CF. Make life easier. Okay. If I make something real, 1, 2, we don't have 4 there, 4, 5, 6, 7, 8. There's 1, 10 there. Yeah. So after 6, we have 8. Okay. 1, 2, 3, 7, 8. So I need, let's say, 10. This is, I'm just changing that. I have almost the same number of tables. Let's see. If the number of labels are same, that means if the elements are same, run it and check. Otherwise, it will give an error. See, you can see that error because here you have more numbers. Shape we have not printed. Let's print the shape. Printed the shape. So let me print the data. Now run. It will again give you an error. Why? You see that this is 8, this is 9. Okay. So you have to increase this. 8. Okay, there 8. I can use this. I can use this. That's okay. It's not a step matching. This is 9. This is 7. What is happening? Predictions. Oh, sorry. Decreasing here. 8. Okay, same. Now the shape is okay. And you can see that all the predicted and the original matches and all the data will fall in the diagram. You can see that. There could be some extra rows, but that happens. You can see that everything is falling in the diagram. So all the ones are in the diagram. Okay. So if the data is same, then it will be okay. Then it will match rather. You can say that. You can play around with the data and you can see that. You can have the weights also. I can give some weights and let's see the weights what we get. We have one matrix here. We have the predicted here and with the weights here. And again, data type is the same. And now when we do the confusion matrix, we give the labels and prediction the weights as WT. The weightage is given like how much weightage is given to uh, which class. You can say that. You can see now. You can see that the weights are now not 1, 2, 3, 4. Okay, it is like 111. It is not 111. Now the weight is this 122, 145, 5, 6, 7. You can see that the values have changed from here. Okay, if we have the same data, then we will not have any issues. 1 minute. The predicted and the original is same, and you will have no issues at all. You will all fall in the same in the diagonal. Major diagonal 1, 2, 3, 4, 5, 6. There is no 7, 8, 9, 10. How the data is arranged. There is no 3. Is 4, 1, 2, 4, 5, 6, 8, 9, 10. This is what it should be. Let's see. And you can see now everything is in diagonal, but it is not 1 now. You have changed the weights. For weights, uh, if nothing is given, then by default the weight is 1. If you are given the weights, then you can see how many, how they are placed. So one will be replaced by the weights or whatever you are giving here. Okay. It's more or less like weightage you are giving to one class. How much weightage you are giving, something like that. Okay. I think everyone is sleeping today. Anyway, continue. Okay, so let's have some data now, and MNIST again will be loading the same data set like MNIST data set, and let's see what happens. Okay, and confusion matrix and all, it will take time to compile, so just put it and just copy paste. This we already have the data. This data we already have. Okay, so I'm just copy pasting from the previous exercise we have done. Number of epochs I have just I think reduced now. That's okay by default. So this is the same data we had yesterday also. So just classes 1 to 10, 0 to 9. This is what we did. We're just compiling it. A small change that is only in the dense layer. That this is 64, 64. The rest shape and all are same. It's the same thing. Just a small change maybe. You'll see how our matrix will be here. We can simply have the matrix and we can actually print it also and see. I'm just putting the code after this so that I don't waste my time. We'll keep on compiling. So we predict with the test images, then get the predicted value shape and the two values, true, y true. Cleaning and testing we have. Then the classes already we have. The inclusion matrix we can generate, and then we can normalize that also, convert it into a data frame and then print it. You see, it will take some time to compile. Epochs, there are not many epochs, but you can see that number of iterations for one. I've used only 5 epochs. So one is done. This is the second one. Have to wait till the 5 epochs are done, or 5 iterations are done. So let's wait. It's almost done actually. You can note down that how the losses, the accuracies are behaving. Loss is decreasing and accuracy is increasing. So 5 epochs are good enough. You can see here the epochs of 5. This is the fourth, and then there will be the fifth one. Fifth epoch, and it will be done. It's a very common practice to have a confusion matrix. It gives you exactly what happened, how the data was classified. It's better to have it. Now the last one, the last epoch, the last iteration, and the accuracy is 99.4. It is still increasing. Uh, Sometimes it decreases. You can see that 99.4, now 3, 6, it's between 3, 6, 5, 7, 5, 6, 7. It is not necessary. Sometimes it drops also. It's not necessary that it will just keep on rising. It may drop also. There may be some overfitting issues. So, okay. So we have now validation accuracy is 98.72, and you can see the previous one was 99.12. Even the overall accuracy is 99.34. That's okay. So 9. Now let's see when we create a, now we don't know the classes, so when we create a confusion matrix, what happens? How the data is distributed. See, the classes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then how the data is placed. You can see that the data is from 0. You can see how it is placed. And that is how we have actually done. Okay, so there's nothing in the diagonals, but this is how we are printing your matrix. It could be the other way around also. You can have like this also. You can have a direct confusion matrix also without normalization, you know. You can have something like this also. You get to label on the two labels, heat map, something like this you can generate. So you need SMS for that. I think I have imported it already. Just yeah, Seaborn. I have already imported, so you use Seaborn for a heat map type of an output. The confusion matrix you can actually just use the predicted value and the original value, and without doing anything, you can get the confusion matrix directly also, or you can just normalize it, put it in a matrix, and then print it. Okay. We have converted into a data frame, so you can see that everything falls in 0. Only one is going out, so you won't get anything on the diagram. You can see everything here. All the classes 0, and they're matching 1, 1, 1, 1. Only 0.2898, and this is 0.02. This is a different type of a matrix because we have converted it into a data frame. We're printing the data frame, we're not printing that. So let me print it and see, show you what we get from here. You may get just output. You just get just the labels, which just says that it is a confusion matrix, but you can see that there, or we can have the normalized matrix also. Like this. This is normalized one. They're all accurately matched. 1, 1, 1, 1, 1. You can see there may be no values in the diagonals because this is how we have designed your matrix. Okay, number classes, apply. We have the labels, predictions. So we can have confusion matrix like this also, or we can have the way we would like the simple labels, predictions, and weights if you want to give them. Just play around and see what exactly suits you. So normally everything will fall the diagonal, but here we have put the classes, so we can see that the data is in the class form. So you can see that here the accuracy is coming on 111.98, so it's fine. Okay, so model or predict text images. What we get here is what is being printed. This depends on how the classes are placed. can see 0, 1, 2, 3, 4. So you can see that everything is matching with 0. Okay. So it is depends on the class matching here, the real form. Okay. Now let's have something else. You'll have application now. Just want to bring introduce LSTM. Just create a new one. I have to share again, no issues. Let me create it first. Okay. I have to stop it and share again. I'll explain it also, but let's see. It is long short-term memory. LSTM, the most common, most widely used model of classification. The algorithm is the most common algorithm, and I'll show you the model how it works. The image here is a very common image of LSTM. Should come. Yeah. We have to just remove the one. There's a lot of data to it. I'll explain how it works. Okay. So here it is called long short-term memory. LSTM. It's a part of RNN only recursive neural network. Most common classification algorithm these days. LSTM, recursive neural network, part of deep learning. Artificial neural network also you can call it. In ANN we have RNN, recursive neural network, and this is a part of that. So if you have some new information, it goes through the sigmoid function. You ignore the things which are not there, that is filtration. Then we have forget gate is very important here. In LSTM, then we select, and then it goes on the loops. It loops, filtered possibilities, collected possibilities, goes back, checks, runs, and then we get the predictions, and that is again passed on. So what we get the prediction from one iteration or one epoch is again passed on to the uh, model, and then again the process goes on till we get the desired output. Okay, so you can see here we have a forget gate. That means it will keep the information inside it, and if we require, it can be used. Like when we are taking the in the first layer, when we pass on the data, so it filters it, and it extracts the features. But suppose some features are not taken and they're ignored, right? They're ignoring few of the features. So my algorithm ignores some features, but they may be useful in the future. So the system goes back, checks, and it corrects from the memory. So there is a forget gate, which is an additional advantage with LSTM. Otherwise, we have back propagation and all that. They are time consuming. They go back, but once done, they lose the information. Okay, so it has a different architecture also that we will see later. But for now, let's see some implementation, and for that, I would be requiring some data. And I already have train.tsv loaded in Teams. I'll take it. Just pasting the thing, what we require, the modules. So it's always a long list, so it's better to use it as it is. So we need numpys, pandas as always, and plotter as always. So in the plotter, we have put the dark background. You can avoid that also. I can avoid it, but let it be. You can see. Now, Kira's processing text, we need tokenizer. Then we need pad sequences. Then we need train and test script to split the data. Categorical classification, we do categorical, we have to convert. Model is sequential. Then the layers. Here we need a dense, dropout, embedding, LSTM, global max pooling 1D, and spatial dropout 1D. So we are calling layers. These are the layers which we'll be using. There are many layers, and you can go through the manual of Kira's, or the Kira's I have already shared the Kira's link, so you can go through that and see that what all other options you have. Okay, so let's have the data first and print it. So we have the train.tsv, and I hope you can get it. I have uploaded here the teams also, but I have it on my system also, so I'll take it from my system. I was using some other data set. Okay, train.tsv. This goes. So we have an option that stays with us. G drive we can upload, and from there we can read. I'll show you. I'll show you later. But for now, let's load this. It's not a big file, but still, it will take some time to load. So here we are just reading a TSV file with a separator /t, and then we are just printing the shape and the data. That's all we are doing. We've imported the modules required. So I can run this. Upload may take time sometimes. It's not a big data, but sometimes it takes little more time than usual. So let's wait for 2 minutes. It should be done. So let's see the data. So we have the sentences, the phrase, the sentiments, which is already there. It's a sentiment data set. Okay. So, okay. Now we have to convert actually. Doesn't take into integer form. The data has to be converted. If you want the classification to be done, they have to be vectorized. So actually ASCII are taken as if there are any ASCII, yeah, we have ASCII, they are taken as hexadecimal, so we have to convert them first. So we have to replace all the apostrophes and all which are there. So we'll write a function to clean them, and we just put a list what we want to clean. So we can use a replace command to clean that, or we can have a replace list. And so this is the data. I am should be I am, RE should be R, let's should be letters. Otherwise, it will just actually like this. It will not take it properly. It will take it as a hexadecimal code, which is not correct. So clean function we call, and in that we convert to lowercase. Then for S in replace list, text if text dot replace, we are just replacing that with the text on the right hand side. Okay, we are not calling it yet, but we have just created the function and kept it. So let's have the training set and the clean training set. Okay, so we are taking the phrase apply lambda. Lambda is an inbuilt is a function which is given inside the local function we have created p, that is clean text. We are passing p to it, the data to it, and p is the data paragraph, data frame, the df frame. And we are just passing the data to it, the phrase to it rather, and this we are reading. Okay, it will be clean now. And then so this is what we get now, the text only. So we have taken just the text and we'll be working on the text. Okay. Let's now we have to split the data. Okay. So extrain dot apply lambda p length split the phrase length of the maximum length we are getting, and we are just printing the maximum length. Here we will be plotting. So you can see that 53. That is the maximum size we have. Let's put a program and see. This is a black theme. We can see background will be black. You can get the sentiment when why. So this is what we get, the sentiment. 0 is the label which was given. Okay. Now we know that it doesn't understand words, so we have to actually convert it into vectors. We have different options, so we can use the tokenizer. First, we have to tokenize that, and then we have to convert it. So you can use methods to tokenizer words and categorical. Sorry, you can see what happens. The word maximum words is 8192. That you can fix. Otherwise, it's okay. You don't want to fix that. It's okay. So tokenizer, we are tokenizing the text, and then we are fitting that on text extrain. This thing tokenizer dot fit on text, then tokenizer text to sequences. Then we are padding the sequences, and then we are converting to categorical. We are converting it categorically. So let's print and see. Extrain. Okay, so this is what we have. Extrain and print by first label only. Okay. Now we have to build the model. We have to define the hyperparameters and build the model. Hyperparameters are parameters which are passed on to the model. Is batch size and epochs are the hyperparameters that model is the building the model only, nothing else. This is model.lstm is sequential, and model.lstm is add embedding input dimension maximum words that we have already calculated. Output dimension is 256, input length is maximum phrase length that we have already calculated. Then spatial dropout is 0.3. LSTM layer we have added here 256, dropout is 0.3, recurrence dropout is 0.3 again. That actually varies. Actually, we'll have to work on it and check. May depend on the data set. Then we have added a dense layer. This is 256. Activation here is ReLU. Then we have a dropout of 0.3. We have kept a 0.3 only. Then again, one more dense layer 5 activation is softmax. That is, I told you yesterday also that our last will always be a softmax layer. If I have the model, I can show you that also. So now you can see this. Okay. All right. I think I've shown the model already. Now we have three things in the while compiling to create the compiler. That is loss function, optimize and matrix. Losses here categorical cross entropy. Optimizer is Adam, and matrix is always accuracy. So this is done. Let me run it. If I don't run, then I cannot actually use. There's some issue here. Max words is not defined. I think I've used max words somewhere. I used it. Yeah, it is there. 8192. I did not run it. Oh, I think. No, I did run it. Otherwise, how will I get the output? Yeah, it's fine. We just have to. Why we have a dropout and just put it here. So dropout is used to avoid overfitting. Now we have to validate. That is, you have to compile. We can use history or something. Any variable here. Model LSTM or dot fit. X train, Y train validation split is 0.10, 0.1, sorry, epochs 8 and batch size 512. It's already given actually. So you can give it here or you can just avoid it. It may take little time to compile. This is an image. These are the phrases actually which we are using, but it should not take much time. There are 8 epochs, but it will take some time. So let's wait, and I'll put English laws and testing laws. These values, you'll have to actually work on it and see what gives you better result. Not necessary, it is not necessary that 0.3 dropout would be good. It may be less, so you can actually work on it, check it, and see. You can vary it and see what is best for you. So it will take little time. Let me put the other code also. There is one more plot. Let's see if I can get. It will take time, so let me do something else. I'll put here what is important. So okay, this is short. A long short-term memory network. So it's a, as I said, it is RNN, artificial neural network. You can say that it is using backpropagation to time and overcomes the vanishing gradient problem. That is loss of data. Basically, vanishing gradient problem is a loss of data. So, so we don't have neurons here. We have memory blocks. It is taking time. So let me explain it till then. So it takes LSTM. Actually, it doesn't use neurons. It takes memory blocks that are connected through layers. So memory blocks will be connected through the layers. So a block has component that make it smart. Okay, then your neurons, which are actually not that smart. So a block would be, you can say, better than the neurons. And a block contains gates that would manage the state, output state, and the output, that is the present state and the output. And then a block operates upon an input sequences, and each gate in the block would use sigmoid activation unit to control and trigger or not, whether to trigger or not, and the changes, and also the additional information which is flowing through the block of, or the through the network, through the model or block, or the conditional block, you can say. So the sigmoid activation units, they control actually the flow of information, you can say, or triggers which are generated. Okay, then we have three gates here, or gate, input gate, and the output gate. Input output is common with all the recursive neural networks, RNNs, right? But here is there is an additional gate, that is a forget gate. This is a conditional gate which decides the information to throw away from the block or just keep it, and it will keep it, and if it is not used for a long time, it will be thrown out. Okay, the data, the information would remain as long as it thinks that okay, fine, it is used. If it is not used for a long time, then it will take it as an obsolete, not required, or an obsolete information, and it will just stop it, throw it off. So it will not just throw it off at the first instance. It will wait for your network to grow, for your network to learn, and once it learns, when it sees that it is not of any use, it will just throw it off. Okay, so we have the input gate is your the data you are putting. Okay. It updates the memory state also, and output gate is the conditional. It's like again conditionally decides what to give the output as, or the desired output you can give, and these are the three blocks we have. But again, output depends on the input and the memory of the blocks. But the forget gate is in between gate, which filters out them and keeps what is relevant. It is taking time. It is time consuming actually. No issues. I'll just put some more theory and see what we can put here. It'll take time. It is slow. And share a link which you can use to better understand. LSTM model. I'll put few things from there. It will keep on growing. This is explained in the link I have shared. So we have different gates. This is sigmoid 10H. Let's see that. This sigmoid layers, 10H layer, then again sigmoid 10H again. See that. This is the data which is passed on. So the link has the details. You want to go into the depths and understand it, then you can have a look at it. And if you want, I can explain it also. Oh, has gone only to the second one. So we'll have to wait. Let's wait. Till that, I'll just stop the recording. There's no point in recording it. You keep on going.